Let's take a look at 118G. The instructions were to use the integral test, and this is the series we're focusing on. Talk about the integral test for a minute. It is on our summary of series tests that we will have on the test. And you can see the integral test here for the series. Basically, if the corresponding improper integral converges, then our series converges. This column right here is the conditions for convergence, right? Our series will converge if the improper integral converges, or if the improper integral diverges, then our series will diverge. So they converge or diverge together. Of course, we do have this situation. All the functions in this example exhibit these three conditions: that the function is continuous, positive, and decreasing for at least some value k, right? X greater than or equal to that value. I do go ahead and just show you that's the case here. You don't have to do this in this case, because the directions say go ahead and use the integral test, but our function is the natural log of x divided by x squared, which is clearly positive for values of x greater than 1. If you remember, the natural log of 1 is 0, and the natural log function is positive for values of x greater than 1. Of course, x squared is positive if x is greater than 1. So that is true. The function's continuous for any value of x greater than 0. Clearly, we're discontinuous. The function is not even defined, right, for values of x that are 0 or negative, because the natural log function, of course, we can't divide by 0 either. So there's a vertical asymptote at x equals 0, and there's no negative values for this function, which doesn't really matter since we're looking at the summation from 2 to infinity. So we're certainly only positive numbers. To show that f is decreasing, it's sometimes a little tricky, because you can kind of see it seems like that's the case, because the x squared function is going to grow more rapidly than the natural log function. But in general, if you want to prove it, you can always take the derivative, and the derivative tells us when a function is decreasing, right, if it's negative. So I do the quotient rule. The derivative of the top, the derivative of natural log, is 1 over x times the bottom minus the derivative of the bottom, which is 2x, right? Derivative of x squared is 2x times the top over the bottom squared. 1 over x times x squared is just x. And then I factor an x out of the top here, out of the numerator. And then I cancel one of these x's here. And I get this expression for my derivative. And this is definitely going to be less than 0 for values of x. I've got greater than 1.65. So how did I do that? I just said, first of all, well, of course, x cubed is positive for any value greater than 0, which we are, or greater than 2, greater than or equal to 2. But 1 minus 2 natural log of x, first of all, when is that equal to 0? It's when 2 times the natural log of x is 1, or when the natural log of x is a half. And that's true when x is e to the 1/2 power, or the square root of e, which is about 1.65. So here's the graph of the natural log function, right? At 1, it's 0. It's going to minus infinity as it approaches 0 from the positive side, and it's increasing on its domain. So right at the square root of e, it's 1.65. So the bottom line is at the square root of e, the derivative is going to be 0, right? Because the square root of e makes the numerator 0, right? That's what I'm solving here. The square root of e will make the numerator 0. And of course, the denominator is positive. So I get 0 there. But for any value of x greater than this amount, all right, what's going to happen? Well, 2 times the natural log of x is now going to be greater than 1, because the natural log of x is going to be greater than a half. Sorry, I've got this wrong. It's not 1.65 there, excuse me. This is 1.65. And at 1.65, that's when the natural log of x is equal to a half, so 0.5. Sorry, that's confusing. So it's a half, but for any value greater than the square root of e, right, the value of the natural log function is greater than a half. And so this difference will be negative. And so the bottom is always positive. And so this statement, this derivative rather, is less than 0, is negative for values of x greater than the square root of e, which is about 1.65. And so since the derivative is negative, the function is decreasing. So all that being said, for x greater than or equal to 2, right, because that certainly subsedes 1, 0, and 1.665, we have got the function being continuous, positive, and decreasing. Okay, which is what we need to be true. Okay, so again, you could have skipped all that, but just wanted to make sure you're clear on that. That's an important part of the integral test, and we know that assumptions do matter. Okay, so now what you were supposed to do is actually use the integral test, and I have a hint in my solutions to use integration by parts, and you'll see why. So first of all, improper integral, just replace, right? We're going to go from 2 to infinity, and I need to rewrite the improper integral with the limit notation, right? So now I can deal with this as a finite interval from 2 to some value t, and I want to integrate natural log of x over x squared. Well, I need to find the antiderivative of that. I don't know what it is, and so I'm going to go and look at just the indefinite integral, get rid of the limits right now, and just find my antiderivative, and that's going to be integration by parts. Remember, Liate is the way I choose my u. L stands for log, I inverse trig, A algebraic, T trig, and E exponential. So the first choice would be logarithmic, and so I'm definitely going to choose u to be the natural log of x, which du is 1 over x dx. My dv has to be everything else, right? The 1 over x squared dx, or x to the negative 2 dx. If I integrate x to the negative 2, what do? I add 1 to negative 2, I get negative 1, divide by negative 1, I get negative x to the negative 1, or negative 1 over x for my v. So remember, here's the integration by parts. Integral u dv is uv minus integral v du. So my u is natural log of x times v, negative 1 over x gives me negative natural log of x over x when I multiply those. And then minus integral v du. Well, v is negative 1 over x. Bring that negative out, I get a positive. I get 1 over x times du is 1 over x dx. So 1 over x times 1 over x is 1 over x squared, or x to the negative 2 dx. Sounds familiar. Just integrated that function a little while ago. What's the antiderivative of x to the negative 2? It's negative x to the negative 1, or negative 1 over x. Okay, so my antiderivative is here. And so going back then, the improper integral will be the limit as t goes to infinity. I now plug in my antiderivative here. My upper limit, if you remember, was t. My lower limit was 2. I plug in the upper limit, t, lower limit 2. And then I take the limit as t goes to infinity. Of course, this part right back here is not going to change. 1 over t is clearly going to 0. What about the natural log of t over t? Well, in one step, we notice that it's going to go to 0 as well. Notice as t goes to infinity, natural log of t is going to infinity. Kind of slow, but it's going to infinity. T is going to infinity. It's in L'Hopital rule form. So using L'Hopital's rule, the derivative of natural log of t is 1 over t. Derivative of t is 1. T goes to infinity. This thing is going to 0. 0 divided by 1 is going to 0. So that limit is 0. So this whole thing is going to 0 as t gets bigger and bigger. And so the limit is just going to be negative this stuff, which is natural log of 2 minus a half, or factor out the 1/2. 1/2 times the natural log of 2 minus 1. Okay, who cares what the actual number is? Just that it's finite is important. So right in the integral test, if the series converges, right? If the improper integral converges, then our series converges. How do I know whether an improper integral converges or not? If this limit is finite, right? This limit is finite, it's not infinity. So because this limit is finite, the improper integral converges, and then by the integral test, the corresponding series converges. And so that's the end of that problem. So a lot going on. You can see sometimes we've got going back to doing our improper integrals and finding antiderivatives. So it's kind of ties everything in together. So I hope this is helpful on this one, which is number 118G.